Okay, so we got this problem, and basically we are given two initial conditions for a temperature of the body in a room, but we don't know the temperature of that body originally. We only know what it's going to be after some time, and our goal is to find the initial temperature of that body. Now, lucky for us, there were some very smart people before us, and they had this equation dt dB is equal to dt divided by dt is equal to negative k tb minus tm. And then tm is the temperature of your medium. So if you look up here, you see the constant temperature of 30 degrees. So the room is in a constant temperature of 30 degrees. So tm is equal to 30 degrees. tb, well, that we don't know, right? We don't know, so we just leave it as an unknown. So we can rewrite our dTB dt equation right here and insert 30 into here. So dTB dt is equal to negative k. We also don't know what k is, right? But we can find out what k is by doing some differential equations. So if we put this differential over here and then get this guy and put it under here, because we want TBs, we want everything TB over here and everything else over here, we get the form dt dB divided by TB minus 30 is equal to negative k dt. That's what we get. And then if you want the solutions here, you put an integral sign on both sides and you integrate. So what we get is we're going to get something like this. We're going to get ln TB minus 30. Right? This is just the natural log. Antiderivative, this is just the natural log. And then this here, this is a really nice, good integral to do. It's just going to be equal to negative kt plus some constant c. Okay. Now, we know that this stuff is our general solution, but it doesn't really tell us that much. We don't know what k is and we don't know what c is, so we need to use our initial conditions. But before I do that, let me just solve for tb by itself. So I'm going to take the exponential of both sides, so e ln tb minus 30 and e to the negative kt plus c. If you do that, what you get is you're going to get the fact that it's just going to become tb minus 30, and that's going to equal to e to the negative kt. Now, exponential plus another exponential is exponential times exponential, if that made any sense. Like, that's just the algebra rule. I might have said that kind of wrong. But just trust me when I say this, you can rewrite your constant e to the plus c as a, and then e to the negative kt, just leave that as is. Okay, so you get tb minus 30 is equal to this. Okay, this is your general setup here. So what you want to do is you want to find out what a is and you want to find out what tb is, right? I mean, you want to find out what a is and you want to find out what negative k is. So you use your initial conditions, and we have two of them. So the first one says that at t equals 0, no, not t equals 0, at t equals 10, at 10 minutes, the body, tb, is equal to 0. And then the other one says at t equals 20, I believe, yes, 20, the body, tb, is equal to 15. So we apply these initial conditions into this equation right here. And what do we get? We get, and we see that negative 30 is equal to A. Yeah, that's it. Right there. Because if we put the 0 here, and then, oh, no, sorry, my bad. We don't get this. Unfortunately, it's a little bit harder than that. We got to put a 10 here. So it's e to negative k 10. I wish it was that easy. Okay, next one. So it would be 15 minus 30. 15 minus 30 is negative 15. And then we get a e to the what? Negative 20k. Okay, so now we can solve for these. We can solve for this stuff. And the way we can solve for this stuff is what we do is we add these two together. Actually, no, let's not do that. We can solve it a little bit easier. So if we just isolate for a, we'll use this one. If we isolate for a, we see that a is equal to negative 15 divided by e to the negative k 20, which is the same thing as negative 15 e to the k 20. Okay, and then we could plug this guy into here. And then you'd see that negative 30 is equal to what? Negative 15 e to the k20 times what? E to the negative k10. And then using your exponential rules, you know that this is negative, my bad. You know this is negative 15 e, and then you're going to add these guys together. And if you add these guys together, you get k10, right? So now you can solve for k, since, look at this, you only have negative 30. So you have negative 30, and you divide by negative 15, and then you get e to the k10 by itself. And you want k10 by itself, right? So what you do is you take the natural log, so you get natural log of 2. So take the natural log of this. It's 30 divided by 15 is positive 2, so natural log. And it's equal to the natural log of e to the k10. And then that drops down, and we just get k10. Okay, so then you could see that k is equal to what? So if you divide out the k, you're going to get ln of 2 divided by 10, and you can write this as 0.1 ln2, which is really nice. So we know what k is now. But we don't know what a is, so we need to do one step farther. We need to kind of repeat this process again. So if we want to go back here, we can use this equation again, or you could use this equation here. But basically, or I'll pick this one too, just to show you. So negative 15, and then a, you don't know what a is, but you know what k is. So you go up to here and you go negative 20, and then k is this, 0.1 ln2. And if you isolate for a, or let me just write this out for you at least, a is equal to negative 20 times 0.1 is negative 2 ln2. Okay, and as you can see, we get negative 15 divided by e to the negative ln2 is equal to a. And then you could write that, that's the same thing as negative 15 e to the ln2. My bad, I forgot negative 2 here. We get positive 2 here. And then, okay, so the way this works, this is negative 15 e, and then ln to the 4. And then you can see it's negative 15. And the natural log can go away. I know I could have made the ln go away earlier, I just didn't, because I chose not to. I don't know, I wanted to make it harder, right? Times 4, which is negative 60. So a is equal to negative 60, k is equal to this. A is equal to negative 60. K is equal to 0.1 ln2. And you could write this, if you wanted, as ln2 to the 0.1. Maybe it looks nicer that way to you. Okay, so now you know the solution to your differential equation right here. So TB, and I'm going to put the 30 on the other side, so it's going to equal 30 plus a e to the negative kt. And then you could write this as 30 plus, and a is what? Well, a is going to be negative 60. And then k is going to be this guy over here. So I'm going to use this one because this just looks nicer. Negative 0.1 ln2. Yeah. 0.1 ln2 t. And you can clean this up and write it as 30, and then 1 minus 2 e to the negative 0.1 ln2 t. And I would recommend just leaving it like this in this form because this looks good enough. So this is your solution, but you're not done yet because you want to know the initial temperature, right? So a lot of work all just to get to here, and then you're not even done yet. So what is the initial temperature of the body, right? Because this is TV. So what you do is you say TV is equal to at time 0, at t equals 0. So then you get 30, 1 minus 2 e, and then this is 0 right here, right? So it's going to be e to the 0. So you get 30, that's going to be 1 minus 2. So you get negative 30, right? Does that make sense? Because if you put the 0 here, you want to find the initial condition of the initial temperature of the body. So you know that when time was 0, You put 0 here. Then this 0 exponential to 0, right? Anything times 0 is 0, and exponential to 0 is 1. So you get 2e to the 0, which is 2. So 1 minus 2 is -1, and TB equals -30. So this is your actual answer. And maybe you should call it in degrees Fahrenheit. Yeah, there you go.